All right, so we've got a pretty interesting question today. So this is Conway's Game of Life. So you guys have probably seen Conway's Game of Life before. If you haven't, well, it looks like this. And what it is actually given in the description here. So the board is made up of a grid of cells where each cell is either alive or dead. And each time that the game updates, they will have these interactions. So any alive cell with fewer than 2 neighbors dies. Any cell with 2 or 3 neighbors lives. Any cell with more than 3 neighbors dies. And any dead cell with exactly 3 neighbors becomes alive. And what we want to do is that given a board, right, we would like to apply all of these rules. Now, to solve this in place, right, because one obvious way you could do this is by creating a whole new board, right, using the old board as a reference of the previous state, creating a new board with the new state, and then just replacing the whole previous board with the new board. However, if we want to use constant memory, we want to be able to solve this in place. Now, since we're given a vector of integers, right, not a vector of booleans, it kind of hints as to how we might solve this. So, to me, the easiest way to solve this is just by using 2 other states, such as 2 equals going to be alive, and 3 as going to be dead, right? So we can sort of have the, actually, we should probably swap these around. So 0 is dead, 1 is alive, and 2 is going to be dead, 3 is going to be alive. Right, so by modifying the board in place, we can store both the original, which is like was alive, going to be dead, was dead, going to be alive. By having all of these states, right, we can store both the past state and the next state at the same time. So actually, I think it's best if we do it like this. Yeah, okay. So let's try it out. So obviously we want to go through every single board. So obviously we want to go through every single cell. So let's create 2 variables. N. I keep on forgetting which one is M, which one is N. I guess for this purpose it doesn't really matter, but we'll just say something like board 0 size. Okay. Because the first time we're gonna be iterating through each board, and then the second time we're going to be iterating through the first time we're going to be iterating through each row, and then the second time for each row we're going to be iterating through each cell. So this would make sense. All right, so one way that we can do it is put a bunch of complicated logic in here, or we can try to move the logic for determining all the rules of the game of life into some helper functions. So let's go ahead and do that. So let's have a function that returns a boolean, obviously, and let's call it survives. Right? Survives. And it takes in a board, just so we know obviously we need the board, and then in I and j, which represent, let's just say the y and x axis, not y and x coordinate, okay, represents a point or a cell within this board. So let's do the current state is going to be board y x. This is the current state of it, and if the current state is 1 or alive, if this is alive, or it can be dead. Now remember, since we're only going to be applying this survives on new cells, we don't have to check for 2 or 3. So honestly, we can just do if. We can just do if cur. Sure, that makes sense. And if it is alive, we want to apply these rules. So we want to get another helper function, right? That returns the number. Since all of the rules, all the rules depend on how many neighbors it has, right? All we want to do is figure out how many neighbors it has, and then there's just going to be a few if statements. So we should create another helper function that just returns neighbors, right? Returns neighbors. So that's given the board and the coordinates to the cell. Let's figure out how many neighbors it has. So we can pretend this works for now, right? Pretend this works right now. Imagine we have the number of neighbors equals neighbors of the board y and x, right? So if, and then we can apply the rules according to this. So if n is less than 2, right? So if our cell has less than 2 neighbors, we're going to return false, right? We return false because our what's it called? We're not going to survive. And actually, instead of survives, we can just call it next state, the int, and now we can use our integer states of 0 up to 3. So if n is less than 2, we say that it was alive but going to be dead, so we return 3. And else if n is equal to 3, I think exactly 3, right? 2 or 3. So n is equal to 2 or 3. We're going to stay alive. So we're going to return 1, which is alive and still going to be alive, or else we return 3. So actually, to simplify this, instead of checking all these like one rule at a time, we can see that these two return the same thing, so we can actually just have one if statement. If n is equal to 2 or 3, it's going to stay alive, otherwise return 3. Okay, and if the cell was originally dead, any dead cell with exactly 3 live neighbors becomes a live cell as a by reproduction. So we say if n is equal to exactly 3, we can return 4, which is not 4, 2, which is was dead but going to be alive. Else, we just return dead, which is 0. Okay, and there's probably other ways to simplify this, but we'll just leave it like this for now. Now, for each, now if we iterate through, all we have to do is just say board I, j, is equal to next state of the board. Pass in the board, we pass in the I and the j as the x and y. And then that's all we have to do, right? We have a very, very simple main function, right? Or not a main function, but this is the function that we call, and then we put all the like logic and helper functions to help separate, right? So we have next state, and the next state requires neighbors to work. So let's implement this right now. So how many neighbors does it have? Well, we run into a sort of interesting issue where if we just get like the board y minus 1 x, right? X minus 1. And then we do this for, however many ones. Y minus 1 or x minus 1 could be less than 0, just like they can be greater than the length of the array, or the dimensions of the matrix. So one way you could handle this, let me just think. Could create another helper, but I think it's fine. First of all, let's let me think. Do a few if statements. I mean, do a few for loops, just to make this code a bit cleaner. So I is less to 1. I is plus. We can have and we can call this I, j. So now this is going to loop 9 times if I equals 0 and j equals 0. We have an int n, which is going to keep track of the number of neighbors, and we're going to return the n here. Now if we'll just write this assuming that we'll never go out of bounds. So I plus so we have y plus I and then x plus j, which is going to go through all of the board's neighbors, right? And I'm going to say if this is equal to let me see, 1 or 3, so 1 or this is equal 3, we're gonna increment n. And then to be a bit cleaner, we'll just say C for cell is equal to this, so we can do that. Now we have to make sure that C stays within the bounds of the matrix. And to do that, we can write more if statements, or we can extend this this guard at the top to make sure both that we don't include the cell itself as its own element, and also if y plus I is less than 0, or y plus I is greater than the board size. This is where it gets a bit messy. I plus j is less than 0, or x plus j is greater than board 0 size. And let me make sure that the board will always, have at least one element. I mean, the dimension is at least 1. We're not going to get a board with nothing on it. Then, that should protect against going out of bounds. And if we try to submit our code, we'll hope we'll hope that it works. Let me just make sure by, running through the program again. We have m equals board size, n equals this dot size. We iterate through. We set each of these to the next state. All right, it doesn't work yet. I almost forgot. Actually, let's just see, right? If we run it, it's not going to work, but hopefully there'll be no errors. There is an error. Why is there an error? I mean, I'm assuming this means that we try to access an array index that was out of bounds. I'm sure it happens somewhere here. But the AND already evaluates first, or let's see, or is less than 0, or plus I is greater than, see, it's greater or equal to board dot size. Let's just try to do that again. And we obviously won't get the correct answer because of this, right? We have the 3s and 2s, which weren't a part of what we wanted to return. We only wanted to return 1 and 0, alive or dead. But you can see every single 3 corresponds to an expected 0. Every single 2 corresponds to an expected 1. So 3, 0, 2, 1. Same thing here, 2, 1. So pretty much we have stored this information of the previous and the next state. Now we just need to turn it back to 0 and 1, right? And to do that, we'll just say if board ij is equal to 2, right? We set it equal to 1 because it is going to be alive again. And if it's equal to 3, we'll set it equal to 0. And I forgot what I copied. I think I just copied this for loop. Oh my goodness. Right. And then if we run it now, we should expect that we get the correct answer. And if we submit to check all the other test cases, you'll see that the code works. So yeah, overall it's an interesting question. There are definitely some better ways you can write some of these functions. Like, for example, instead of just having like a comment that explains what each of these integers mean, this is like a prime example of why you would use an enum, right? So for example, you have an enum, what should we call it? Enum state, and the first state is dead, dead, then dead. We have alive, then alive. I don't know if this is the proper. Okay, whatever. And then we have dead, then alive, and alive, then dead. Right. So replacing all of these, like they call them like magic numbers, right? We have no idea what 2 and 3 or 1 or 0 means unless we look at, this comment. But being able to have an enum like this, we can sort of replace these. Like if the actually this is the number of neighbors. Yeah, that's fine. Then here we can return alive, then alive, here alive, then dead, right? Dead, then alive, or dead, then dead, right? It's like this means makes a bit more sense, just like how here we can check if the board was equal to dead, then alive, right? We return alive. And if it was alive, then dead. Now it's just gonna be dead. Anyways, I started yapping. Yeah, there's not much left to be said. You know, there's all sorts of ways you can write the program. And at the end of the day, the important thing is that you recognize a solution. You're able to, you know, break them down, either write them in a nice way, right, in a you know, very neat, concise way, or if you can't do that, or you don't have the time to figure out how to write it in a concise way, you know, just break it down to helper functions, right? So each individual function is easy to read and comprehend, right? So for example, this game of life function, it's very easy to read this and be like, hey, all we do is, you know, what we can do is set each board cell equal to the next state that it should be in, given the, you know, whatever this function returns. And then after that, we can set all of the states from, you know, if it's dead then alive, set it to the actual alive state, right? If it's alive then dead, set it to the actual dead state. And then, you know, the next state, you're just be like, hey, we get the number of neighbors, we apply the rules to alive and dead cells. And of course, count neighbors looks terrible, but you can sort of tell this is just to stop it from going out of bounds. And if we have a neighbor that is alive, which is, alive then alive, or before it was alive then dead, because we're using obviously the previous state. Yeah, we count that as an alive neighbor. So yeah, that's pretty much the video. Hope you guys enjoyed. Let me just resubmit this new code. I don't know if you can, I don't think you can define an enum within the class. That doesn't make much sense, but we'll do this. This is accepted. Yeah. So yeah, that's gonna be the video. Hope you guys enjoyed it. Leave a like, subscribe. I'll be making more videos soon on more interesting topics, probably. I'm getting kind of tired of doing LeetCodes. Yeah, that's it.